How do you understand quality factor, Q, in inductors and capacitors? Imagine tuning a radio to catch a clear signal. The clarity depends on how well the circuit can store and transfer energy. That's where the idea of the quality factor, or Q, comes into play. It's a way to measure how efficiently an inductor or capacitor can store energy without losing too much as heat. In an electrical resonant circuit, like one with an inductor and a capacitor, energy moves back and forth between the magnetic field in the inductor and the electric field in the capacitor. But some energy gets lost each cycle, mainly as heat. The Q tells us how much energy is stored compared to how much is lost. If the Q is high, it means the device holds onto energy longer and loses less. If it's low, energy dissipates quickly, and the circuit dampens faster. For inductors, Q is calculated by dividing the inductive reactance by the resistance. The inductive reactance depends on the frequency and the inductance value, and it shows how much the inductor resists changes in current. Resistance is mainly from the wire used in the coil and any core losses. So, a high Q in an inductor means it has low resistance compared to its reactance, making it better for filtering and tuning. Capacitors also have a Q, which is the ratio of their capacitive reactance to the equivalent series resistance. The capacitive reactance depends on the frequency and the capacitance value. The ESR accounts for dielectric losses and other internal resistances. A capacitor with a high Q stores energy efficiently with minimal heat loss, which is vital in circuits like oscillators and filters where precision matters. From a broader perspective, Q relates directly to the bandwidth of a resonant circuit. The bandwidth is how wide the circuit can pass signals around its resonant frequency. The higher the Q, the narrower the bandwidth, meaning the circuit is more selective. This is useful in radio and communication systems where picking out a specific signal is important. In practical terms, a high Q in inductors and capacitors improves the performance of RF circuits, filters, and oscillators by reducing energy loss and increasing selectivity. But if the Q gets too high, the circuit can become sensitive to temperature changes and component variations, which might affect stability. To sum it up, the Q factor in inductors and capacitors is a measure of how well these components store energy compared to how much they lose. It's calculated by comparing reactance to resistance or ESR. A high Q means less energy loss, sharper resonance, and better performance in tuned circuits. It's a key parameter in designing efficient electrical systems that relying on precise energy transfer and filtering.